So next up, we really need to understand light and the atomic spectrum because they're greatly related and it's how we understand almost everything we know about the cosmos. So what is light? Well, light is defined as an electromagnetic wave, but visible light, what you think of as light, is only one tiny portion of the electromagnetic spectrum, okay? It contains energy. It is electrons in the ground state absorb the energy and then they release it as light. So it is a particle, but it's not a mass. It's not a particle with mass. It's a massless particle called a photon. Thanks to Einstein, Albert Einstein, we understand that there is a duality to light. It acts like a wave, but it also is a particle itself that we call a photon. And those are all released by atoms. So everything that has mass has the potential of releasing a certain amount of an electromagnetic wave, that's energy, in a photon form. And so what we get is the electromagnetic spectrum, and that's where all of that energy, all of that light really is. Notice that it's much more than just visible light. And in fact, the spectrum can be thought of in a number of ways, not harmful to harmful, getting more dangerous as you go across, or larger wavelength to smaller wavelength, or lower frequency to higher frequency. Any way you think about it, it's all the same thing. It's all photons. It's just different amounts of energy in them. And the energy definitely increases as you move this way on the electromagnetic spectrum. Now, that's important to note because all of visible light is here. But there's plenty of things we know about that aren't in visible light that are on the electromagnetic spectrum that are still light. For instance, radio waves, the fact that we can hear the radio, well, those are the weakest of the waves. In fact, they're really, really big. Their wavelength, or the distance between those two wave peaks, would be about the size of a skyscraper if you think about it that way. Notice right here, though, I find this one interesting because so many people always fuss about microwaves. Well, microwaves are actually less harmful than visible light is. What's special about your microwave is the box that keeps them all in there. Then we have infrared. Then we start to get into more difficult things, ultraviolet, X-rays. You know, enough of those can harm you. That's why they use a large shield for important areas when they do them. And then gamma, the stuff of nuclear radiation. Even those colors that we think of are all there in that visible spectrum that are made of light. They're just different amounts of wavelength or different frequency and different amounts of energy. Lowest energy is actually red, highest is ultraviolet. If you've ever played around with a laser pointer, if you had one that was red, it was fairly weak. If you had one that was green, it was getting better. But if you got a blue to an indigo one, those are really powerful laser pointers. In fact, anything that has that much energy can start to be used to where it can actually do a small amount of burn or popping balloons, which is kind of fun. Like I've stated before, all of these equal either wavelength or frequency that you want to think about it. A long wavelength or a large wavelength has a low frequency, low energy. Short wavelength or a small wavelength is high frequency, high energy. But all of them move at exactly the same speed, the speed of light, 3 times 10 to the 8th meters per second. It's really, really, really fast. So if you think about it, it's around 670 million miles per hour. But I'm sure you're wondering why I need to know this in a chemistry class. That sounds like physics. Well, it is physics, but it's the physics part of chemistry. There's a lot of physics in chemistry if you start to look at it. But what's important to us is the fact that all of this electromagnetic light comes off of atoms because energy causes those electrons to jump to different shells, different electron orbital paths. We refer to those as N1 or different states. N1 to about N7 as we look down the periodic table. And as they jump up, they then want to go back to their normal 1. So that energy is put in, they absorb it, it is an excited state, moves the electron up one, or however many it moves it up. And then it will release that photon when it snaps back and it shoots out that energy in the form of a photon packet. And depending on how it jumps, where it jumps, how much it jumps, or what electrons are there to jump, will depend on what kind of electromagnetic wave it sends out in the visible spectrum. This is vastly important to us because we've actually proven this over and over. If you look at things like this, these are certain gas tubes. Notice all of these are noble gases: neon, argon, krypton. All of these will actually produce, I imagine that's helium, will produce a different color of light when they're excited. So when we put electricity or energy into it, we end up getting an excited state for these atoms in their gas form. And when you look, you get a different spectral line. So it doesn't give you a full spectrum where you get the full rainbow. You get slits of light that show up depending on what element is there. In fact, every atom has a unique signature of light that it produces because of this. And that means we can identify just by the light that it has what atoms are there. So remember last time we were talking about fusion happening in the sun with helium and hydrogen. Well, we know this because of the light that we get off of the sun. In fact, we can judge how much hydrogen and how much helium. It's about half and half right now, so we know that our sun is about halfway through the conversion process of moving hydrogen into helium. But it's used in a number of different ways, and it's able to figure out all kinds of stars and cosmos things, and what things are made out of, where we can't actually reach them, but we can see the light from them. Again, this is important to us because we're looking at that quantum, the amount of energy that is absorbed by an electron when it moves up one higher energy level, so like from N2 to N3. And then when it snaps back, it releases that amount of energy in the form of that photon. Here's a better visual of that though. So we're using more of a Bohr model of a hydrogen atom, okay? And so hydrogen would only have electrons in this N1, but depending on the amount of energy and what happens, it can excite that electron into different places in different energy levels. But it's unstable because it wants to fill up that lower level, that N1. And so it eventually snaps back, but it has to release that energy that excited it in the first place. And so we get that photon light. And because of that, we can get all of this electromagnetic spectrum, only this tiny sliver of which is visible light. And here you can actually see it being red to violet, or red to indigo, depending on who's writing it out there. And you can see that their wavelength is decreasing as it moves along. These are listed in wavelength. Up here, it would be the wavelength measured in meters that you can see. And so it only happens between this little spectrum that we have any visible light at all. So this explains a great number of things. It's why you can get some groovy looking lights if they have a different gas inside them. If we burn different elements, they come up as different colors. In fact, that's how we get fireworks. There's different elements inside them that it explodes or is ignited, and so it's excited and releases these different colors. It's greatly helpful and greatly fun. Hope that helps.